In this video, we'll look at VSPER theory and the three-dimensional shapes of molecules. VSPER theory, or valence shell electron pair repulsion theory, describes the shapes of the molecules. It helps us predict the arrangement of the valence electron pairs around our central atom. And it states that they arrange themselves around the central atom to minimize their mutual repulsion and produce the lowest energy arrangements. So everything, our lone pairs and other atoms, are going to be arranged around the central atom to be as far apart as possible. And this way, they reduce their electron repulsion. And so some different shapes we're going to look at will be linear, bent, trigonal planar, trigonal pyramidal, T-shape. There are going to be many more shapes beyond these, but these are some that we'll start to look at. Now, looking a little more closely at VSPER theory, each group of valence electrons around the central atom wants to be as far apart as possible. And when we talk about a group, our quote-unquote group of electrons is any number of electrons that occupy a localized region. So that means single bonds, double bonds, or triple bonds still count as one group. So even though a triple bond contains 6 electrons, it still counts as a single group. Lone pairs count as a group, or a single electron will also count as a group. So remember, each group is just kind of the localized region where those electrons are. Now let's talk about the different types of groups. So first, we have our electron group. That's the region around the central atom that the electron pair resides. So these are our bonds and our lone pairs. Getting a little more in detail, we have bonding groups and non-bonding groups. Our bonding groups is the region between two atoms that are occupied by electrons involved in a covalent bond. So the bonding group, as the name implies, is the bonds between our two atoms. Our non-bonding group is the region occupied by non-bonding electrons, or lone pairs. So it's important to remember these two groups. We have bonding groups, or the bonds between the atoms, and non-bonding groups, or the lone pairs. And we use those two groups to figure out the shapes of our molecules. So looking a little more closely at our example atom here. Looking a little more closely at our example here. Here we have atom A, and it's bonded to 3 different atoms and a lone pair. So if I want to figure out the number of electron groups I have, so remember, that's the big overall umbrella. The electron groups are the bonding groups and the non-bonding groups. So this is going to be all of our different groups together, bonding plus non-bonding. So if I look at atom A is bonded to 1, 2, 3 different atoms. So I have 3 bonding groups. And then there's also a lone pair. That lone pair counts as a non-bonding group. So that means atom A has 4 electron groups around it. One thing to note, it doesn't matter that there's a double bond here, it's still bonded to an atom. So remember, the electrons in the double bond here, they're in a localized region next to each other. So that's why they still count as just one bonding group. Not too bad, right? Add up the number of atoms around it, add up the number of lone pairs. Once we do that, then we can start talking about our shapes. So our electron pairs, whether they're bonding or non-bonding, repel each other because 2 negative charges always want to repel each other. And so by assuming that these electron pairs are going to be placed as far apart as possible, we can start to predict our shapes. And the amount of groups we have will start to help predict our shapes. We can have linear, if we have two groups, they'll get put as far apart as possible. Trigonal planar, tetrahedral, trigonal bipyramidal, and octahedral. Looking at one last thing with our electron groups and our electron group geometry. First, we want to count the number of electron domains. So I want to count how many groups I have. That's the bonding plus the non-bonding. And for that, we have to draw its Lewis structure. So we have to draw a good Lewis structure for the molecule. Second, the geometry will correspond to the number of electron domains or electron groups. So if I have 6 things attached to my central atom, the geometry would be octahedral. If I have 4 things, the geometry would be tetrahedral. And one important thing to note, the electron group is often not the shape of the actual molecule. So we have electron group geometry, and we also have molecular geometry. The molecular geometry is defined by positions of the atoms only. So we only look at the atoms when we're talking about molecular geometry, not the lone pairs, not the non-bonding pairs. So electron group geometry, that's our bonds plus lone pairs. Molecular geometry, that's the bonds only. But we use the electron geometry, we use the electron group geometry to help us figure out the molecular geometry. And so looking at these non-bonding pairs, the non-bonding domains are always physically larger than the bonding domains. And that's because the electron pair always wants to be as far apart as possible, and they don't have another nucleus next to them to constrain their size. So most lone pairs have a greater repulsion, which tends to decrease the bonding angle in our molecule. And we can see this if we look at the bonds between the hydrogens in 3 different examples here. So our bond angle is formed between 3 different atoms, our top one, our central atom, and another outer atom. So between these 3 angles, we can come up with our bond angle. Sorry, between these 3 atoms, we come up with our bond angle. And so because the lone pairs take up a little more space, they're actually going to squish down those hydrogens and make them go a little closer. So if we look at methane here, CH4, we can see there's no lone pairs on our central atom. So all the hydrogens are 109.5 degrees apart from each other. That's their bond angle between these 2 hydrogens, between these 2 hydrogens, between these 2 hydrogens, and also between these 2. They're all 109.5. Once we add 1 lone pair, the bond angle changes. So if you look at ammonia here, the nitrogen has a lone pair, and then all the hydrogens are kind of squished a little further down together. Their angle actually happens to be 107 degrees. And then if we look at water, having the 2 lone pairs in water pushes the 2 hydrogens even closer together. So the bond angle for the 2 hydrogens in water ends up being 104.5 degrees. So you can see it's not much of a push, but there's still a little bit of a change in the bond angle when we add lone pairs. Now that we know about our lone pairs and our electron domains, let's start looking at molecular geometries. For the molecular geometry, we only consider the bonding groups. That's all we care about is the bonding groups, nothing else. I don't care about the lone pairs when I look at molecular geometry. So what we do is we first figure out the electron group geometry based off of our Lewis structure. Then we figure out the molecular geometry. And there could be more than one molecular geometry for an electron group. So here we have tetrahedral. Tetrahedral has 4 electron groups attached to it. With those 4 electron groups, to get them as far apart as possible in 3-dimensional space, it becomes a tetrahedral, where a central atom is kind of floating up a little higher than all the atoms on the bottom here. And so this could be something like our methane that we saw on the previous slide. If I remove one of these atoms and I replace it with a lone pair, I end up with trigonal pyramidal. So now I have 3 atoms bonded to it and 1 lone pair. Since we don't consider the lone pairs when we do molecular geometry, nothing gets put at the top of the pyramid here. And this could be something like the ammonia that we just saw. And then finally, if I remove a second atom, now I have a bent shape. And you can see it kind of looks bent between my three atoms here. There would be a lone pair here and here. And this could be something like the water we just saw. So you can see for molecular geometry, all we do is we start with the electron domain geometry or electron group geometry, and then start removing atoms, and we get our different molecular geometries. Now let's look at these actual groups and the different ones they make. So here we see the first three possibilities. We see when we have two groups, three groups, and four groups. So if we have two groups, have two things attached to that central atom, it has to be linear. The best way to get those two things as far apart as possible is to make it linear. So I'd have one group on one side, second group on the other side. That's all I can do. Remember, we need three atoms to make a bond angle. So here I have it linear. So if I have two groups attached to my central atom, linear. That's it. That's your only choice. Now it gets a little more interesting when we look at three groups. If I have three electron groups attached to that central atom, if they're all bonding groups, so I have three atoms attached to it, I have something called trigonal planar. And the angle between all of these, that's 120. So that's 180. And then if I replace one of those atoms with a lone pair, now I have a V shape or bent shape. So now we have a bent shape. And the angle is slightly less than 120 because of that lone pair repulsion. But so for our three group geometry, trigonal planar, we can either have a trigonal planar molecular geometry or a bent shape molecular geometry. And then now you can see when we have four groups, we end up with a tetrahedral. If all four of those groups are bonds, so I have four atoms, then I'd have a tetrahedral shape. If I have three bonds and one lone pair, we end up with trigonal pyramidal. Now this is slightly different than a trigonal planar. Here, all the atoms are in the same plane. This is flat. With this one, the central atom is actually raised up a little bit. So the central atom sits up a little bit higher than these other atoms. And then when we have two atoms bonded, so two bonding domains, we again end up with our bent shape. Not too bad for these, right? That makes sense. That's pretty easy. So now let's look a little more at 5 and 6. So these are the ones that have to break the octet rule. When we have 5 groups, we end up with something called trigonal bipyramidal. You can kind of see we have our central atom, 3 atoms are in the same plane making a triangle, and then I have another atom on top and another atom on bottom. This is the most stable configuration for trigonal bipyramidal, for when we have 5 groups attached. It makes a triangle around the central plane, and then it turns into a pyramid on the top and a pyramid on the bottom. So if all 5 of those are bonded together, we end up with trigonal bipyramidal. This could be something like PF5. All 5 would be bonded together in this case. All 5 fluorines would be bonded around that central phosphorus. If we replace one of those atoms with a lone pair, we end up with 4 bonds, or what we call a seesaw shape. So it kind of looks like a seesaw if you put this part on the ground, and then these can almost rock back and forth like a seesaw from a playground. And then if we have 3 bonds, we end up with a T shape. So I have my top one, my bottom one, and still one along the central plane. That makes a T. And then finally, if we have only 2 bonds, we end up with linear. So I just have the top and the bottom. All 3 domains along the central plane, all of those are lone pairs. Now, before we get to the octahedral, probably asking, why did I pick the central plane to put the lone pair? Why not one of these on the top? Well, the answer has to do with part of the geometry. If I have my equatorial ones all here, all those equatorial ones are 120 degrees apart from each other, right? So everything here is 120. And then between the axial and the equatorial, that's 90 degrees. That's a smaller angle. So my lower energy configuration results from having the non-bonding electrons equatorial. Because if I make one of these a non-bonding, hey, that non-bonding is 120 away from at least 2 other atoms. If I make this one the axial non-bonding, then it's only 90 degrees away from all the other atoms. So that's why we make the equatorial ones the non-bonding, so that there's more space for that lone pair to occupy. So finally, looking at our 6 electron groups, our largest ones. For the 6 electron groups, if I have 6 groups around my central atom, again, I have to break the octet rule for that to occur. Now I have 6 different spaces to occupy. 4 of them are around the same plane, the central plane, and then I have 1 on the top and the bottom. And this makes our octahedral. If all those 6 are atoms connected together, so I have 6 bonds, then I end up with the octahedral shape. If I have 1 as a lone pair, then I have 5 bonds. And that gives me square pyramidal. If I have 4 bonds, that gives me a square planar. All 4 in the central plane are my bonding ones, and then my 2 axial ones are the lone pairs. So in the case of octahedral, it doesn't really matter which one we pick to make the lone pair. All of these angles here are 90 degrees. Whether it's axial or equatorial, they're all 90 degrees apart from each other. So now let's look at some examples of all these different ones. Here we look at our first one. It's linear. With the linear one, some examples: CS2, HCN, BF2, BEF2. All of these exhibit a linear molecular geometry. You can see that central atom will be bonded to just 2 other atoms. If we look at trigonal planar, examples for a trigonal planar, if all 3 are bonded to atoms, that could be SO3, BF3, NO3 minus nitrate, or carbonate, CO3 minus 2. All of those would exhibit a trigonal planar geometry. Or if we switch out one of those bonding groups with a lone pair, we can end up with SO2, ozone, lead-2 chloride, or tin-2 bromide. Those are all examples that exhibit a bent shape. Finally, when we look at a tetrahedral, this is when we have 4 groups around the central atom. If all 4 of those are atoms, we have CH4, silicon chloride, sulfate, perchlorate. Or if we replace one of those central atoms, if we replace one of those atoms with a lone pair, we end up with trigonal pyramidal. Examples would be NH3, PF3, ClO3 minus, or H3O plus. Now, if we have two lone pairs and two bonding pairs, that gives us a bent shape. We can have water, oxygen difluoride, sulfur dichloride. And looking at our other ones where we have our expanded octet, so we'd start with trigonal bipyramidal. If all 5 of those are atoms, could be PF5, ASF5, SOF4. If we replace one of the atoms with a lone pair, so we end up with a seesaw shape, could be SF4, XeO2, F2, IF4 plus, IO2, F2 minus. Now, if we have two lone pairs and 3 bonds, so I have two lone pairs and 3 atoms, that could be ClF3, BrF3. Those are some other examples for that one. Other ones, if I have just 2 atoms attached to it, it ends up being linear. And then I have 3 lone pairs around the central atom. That could be XeF2, I3 minus, IF2 minus. You can see we're getting into the more exotic, interesting configurations when we get to our expanded octets here. And finally, looking at octahedral. In octahedral, remember they're all 90 degrees apart. I have 6 atoms or 6 bonds around the central atom. So this is an expanded octet. Ones that exhibit an octahedral setting is when I have 6 atoms around it. That could be SF4, that could be SF6, IOF5. Those are a couple examples there. Other ones, if I replace one of those atoms with a lone pair, I have square pyramidal. So you can see it's a square, it's in a pyramid shape. It could be BrF5, TeF5 minus, XeOF4. And then finally, I can end up with square planar. With square planar, I have 2 lone pairs and 4 atoms around the central atom. And 4 atoms around the central atom. Examples of that could be XeF4 or ICl4 minus. So now you guys should be able to start figuring out your electron domain geometry, electron group geometry. And then also once you know the electron group geometry, which you figured out because you're able to draw a Lewis structure, then you can go and figure out the molecular geometry, figure out the actual shape of the molecule. And with that, remember, we only look at the atoms that are bonded to it. The lone pairs don't count when we're looking at the molecular shape.